Hello students, today we will move to our second module in our subject compressible fluid flow. So this module deals with isentropic flow. Okay, this module deals with isentropic flow. So you guys know what actually is isentropic flow is meant by. It is nothing but a flow in which there is no heat transfer. So there is no heat transfer means the flow is adiabatic. So all adiabatic flows won't be isentropic. Only a reversible adiabatic flow will be isentropic. So reversible means there is no friction or friction loss. So such case of flow are termed as isentropic flow. So before that, students, you have already learned the basic different governing equations for a compressible fluid flow. Governing equations. So what are the governing equations? First one, mass conservation, right? Mass conservation. Second, conservation of momentum conservation. Third, energy conservation or first law of TD, energy conservation. Fourth one, fourth one, second law of TD, second law of thermodynamics, that is regarding entropy. Okay, so these are the four different governing equations. These are the basic equations which govern the various phenomena associated with the compressible fluid flow, right? So students, you have already learned all these equations in your first module. So students, but you know the complexity of equations involved in this analysis, the complexity of all these four different equations, right? So all these four different equations involved in the analysis of our compressible flow, right? So these four equations are much more complexer than those associated with incompressible flow or those that you have studied in your fluid mechanics, right? So the integral and differential form of these governing equations for a control volume are highly a kind of non-linear set of equations, right? So they are differential, they are partial differential, they are non-linear set of equations both in space and time. And how to solve that equation? To get some general solution for those equations practically non-existent, right? So students should note that those equations are highly non-linear. Non-linear means with a higher degree. Okay, linear means if x plus 2y is equal to 0 is a linear equation, right? X square plus 2y plus z square is a non-linear equation in a second degree equation. That's the difference between linear and non-linear. So our governing equations are non-linear equations. Non-linear set of equations, partial, they are even partial differential equations, not algebraic equation, they are partial differential equations in both space and time, right? Space and time. Space means x, y, z, the independent variables are x, y, z, and time t. So this much four different variables are there. They are partial equation, they are non-linear set of equations. So not getting a general solution for these equations are practically impossible, or it is very difficult uh, at a stage at current stage of your study. It is impossible to find solutions for this kind of equations. Solutions are there. You can apply complex CFT methods or different you have heard of computation fluid dynamics and all, right? So there are methods, but at this stage of study, it is impossible for you guys to get a solution for this kind of equations. So what will you do? So in order to simplify these equations, we apply some assumptions, right? So in order to make them solvable, these equations are simplified by making certain simplifying assumptions. In order to make these equations solvable. We simplify those equations by what? By applying assumptions. Okay, by applying assumptions. So what are the assumptions we apply? First one, we apply the approximation or assumption that it is approximated as steady flow. The flow when the flow is approximated as steady flow, what will happen? That there is no steady flow approximation. It signifies that the magnitude of the flow properties at any section do not vary with the time. So time is not a variable here. So any property at any cross section does not vary with time. So that is the significance of steady flow approximation. So in order to achieve a steady flow, the fluid particles must have to move along straight lines. Even though in real flow there may be turbulence which make the flow somewhat unsteady, but the solutions to these problems based on the steady flow approximation deviates only little from the real situation. So we can approximate this streamline flow as steady flow, right? So that we can avoid the presence of time as an independent variable. So we have removed time. Second, one-dimensional flow. We can approximate it as one-dimensional approximation. One-dimensional approximation means what? One-dimensional approximation means we can approximate the space variables to only any one of them. We have three different space variables x, y, z. One dimension means we can approximate as either x, either y, or either z. So that is one dimensional approximation. Third one is negligible body force. Negligible body force. So this approximation is regarding body force. The body force is always proportional to the mass of the fluid contained in the control volume, right? So since the flowing fluid is a gas, the force due to the mass of fluid contained, the force due to the mass of that fluid contained within the small control volume at any particular instant may be very small and can be reasonably neglected, right? Hence these approximations make only insignificant deviation from the real situation. So have you understood? The body force are those forces associated with the mass of the flowing fluid. Since we are deriving equations based on a small control volume at any instant have very small mass of fluid. The force due to this mass of fluid may be very small. It can be reasonably neglected. So negligible body, that is by using this kind of approximation, this approximation makes only very insignificant deviation from reality. So this can be applied. And the fourth approximation is perfect gas approximation. Perfect gas approximation. So the flowing, we are dealing with the gases. If you approximate it as perfect gas, we have many uses. The flowing fluid is assumed to be thermally and calorically perfect. So the gas is thermally perfect means R can be the universal gas constant. It can be a constant. If it is perfect gas, R is constant, and the internal G and enthalpy are functions of U and H are functions of temperature only in case of a perfect gas approximation. If it is not perfect gas, it may sorry, okay. If it is a real gas, it won't be function of T only. Some pressure and volume will also come into play, right? So these are the advantage of approximating it, the flowing gas as perfect gas. Okay. And in case of perfect gas, Cp and Cv are constants. They are independent of temperature. In case of real gases, Cp and Cv are functions of T. So for the range of property variation of of interest to us, the range that we are interested in, the deviation due to perfect gas assumption is very little. So perfect gas approximation is applied. So these are the four different assumptions we are using. Okay. So students, another concept called simple flow. So what do you mean by simple flow? So after applying all these four different governing equation, we can even simplify it by more assumptions. Okay, so by steady one-dimensional flow approximation, the complexity of the governing equation can be reduced by a great extent. But the resulting equations are the governing equations for a generalized steady one-dimensional flow. After applying 1D or one-dimensional steady flow, after approximating the flow as one-dimensional steady flow with negligible body force and and the gas as approximating it as perfect gas, we get a simplified general equations, governing equations, but still the complexity is higher. Why? Because these resulting equations are governing equations for a generalized steady one-dimensional flow of a perfect gas. But these equations are still complicated for obtaining a general solution, general closed form solution, because they involve several independent driving potentials. Okay, still complicated. Why? Still complicated. Even after the approximation, after those four approximation, still the equations are general equations only. That is why still it is complicated. Why? Because there are different factors, because they involve several different independent driving potential. Still several independent driving potentials are there. Driving potentials are involved. So students, what do you mean by driving potential? In your HMT class or in heat and mass transfer class, the heat transfer is taking place due to a driving potential of what? A temperature gradient or a temperature difference. So temperature difference is a driving potential for heat transfer. Similarly, for mass transfer, there is a concentration gradient, difference in concentration, right? So that is a driving potential. Similarly, for fluid flow, pressure difference is a driving potential. So in our case, this is a compressible fluid flow. There are four different driving potentials. First one, area change. Area change. So area change is a very important driving potential for compressible fluid flow. Even if even if we are approximating the general flow, the flow equations to one-dimensional steady perfect gas flow with negligible body force, still the driving potentials are maybe area change. Area change is a driving potential too. Friction can be a driving potential. Third, heat transfer can be a driving potential. Fourth, mass addition. Okay, so these four different flow situations are there. So flow situations in practical cases may involve the simultaneous effect of all these four driving potentials. Okay, so in order to make the study even simpler, we will take the cases separately, where only one of these four driving potentials are acting, and we will neglect the effect of all the other three. So we will study different types of flow with different driving potential. We won't take all these four together. We will be able to take all this four together only after analyzing the effect of all these four different separately. Then only we can study the effect when all these four are present simultaneously, because it involves a more complex analysis or complex calculations and all. So for the time being, we will start with the basics, the very fundamental type of flow. So those flow in which only one of those driving potential is taken into care. Such flows are called simple flows. Simple flows are those flows with only one driving potential is studied, right? Right. So there are four different driving potential flows where there is a gradual area change. They are usually called isentropic flow. Second one is flow with the friction, usually called fan of flow. There is a flow with heat addition, it is called Rayleigh flow. Flow with mass addition, it doesn't have any particular name. So I will mark it. First one, the flow with area change is isentropic flow. There is no heat transfer, there is no friction, there is no mass addition, only area changes. Okay, since there is no friction yes, there is no friction means the flow will be reversible. There is no loss due to friction. There is no heat. There is no heat transfer means adiabatic. Reversible adiabatic processes are isentropic process, and only the driving potential here is area change. So this type of area change, if area change is only driving potential, this type of flow is also known as isentropic flow. Second one is friction, flow with the friction. So here this flow is called fan of flow. Third one is diabatic flow. That is, there is a heat transfer, not adiabatic. It is diabatic flow. This flow is also known as Rayleigh flow. And fourth one is flow with mass addition. So students, we will learn all these four different type of simple flows in our coming chapters or modules. Each module is devoted for each kind of this particular flows. Okay. So in the second module, we will be learning area change, the flow where there is a gradual area change or isentropic flow. And coming modules, we will be learning fan of flow, Rayleigh flow, and flow with the mass addition. Okay. So hope you have understood the basics of this simple flow. So these are four different simple flows. Okay. Simple flows are classified based on the basis on the basis of what? Driving potential. So what actually is the what actually causes the fluid to flow? That is called driving potential. Students, here no friction, no heat transfer, no mass addition. So that is why, so no mass addition, no friction, no heat transfer means adiabatic flow. No friction means there is no loss due to friction, so the process will be reversible. No mass addition means there is no incoming heat or work with respect to mass that is being added. Okay, it is not inducing any kind of energy with the mass. So it can be an isentropic flow. Isentropic flow means reversible adiabatic. So reversible adiabatic and no mass addition. So this can be isentropic flow. So what is the only driving potential for the property changes in the flow? Only driving potential is area change. Very important. Area change. Area change means what? If it is flowing through a fluid, a conduit, a sudden gradual increase or gradual decrease. Gradual decrease. So this gradual increase or gradual decrease in the path of flow, or the conduit of the flow, is the driving potential for the compressible fluid to flow. Okay. So that is the only driving potential. Or rest all the other three driving potentials are ruled out, or they are considered as negligible. They bring about negligible changes in the flow. So this chapter is devoted. This module is devoted for the discussion on the nature of flow process, and also to derive some equations of practical importance from the governing equations for steady one-dimensional isentropic flow. Okay, what is it? Steady one-dimensional isentropic flow of a perfect gas. So these are the assumption. It is steady, it is one dimensional, it is perfect gas, there is negligible body force, and the flow and the driving potential is isentropic, the area change. So that is why it is called as isentropic flow. Okay. So students, you have learned about the conservation equations or governing equations already, right? So before moving to conservation equation, what is the purpose or application of the application of study of this particular isentropic flow? The equations or the concepts developed, concepts studied in this module has got very great practical value in analyzing many real flow situations, particularly in duct flows, right? So because in duct flows there may be gradual variation in the flow cross section or area of cross section, right? So what are the basic example for this type of flow, or where there is where we have a lot of change in or gradual change in cross section? No, nozzles. Have you heard of nozzles and diffusers? Nozzles are those ducts or those conduit which gradually just got gradual change in cross section. It gets its area reduced so that velocity gets increased. Diffusers are actually having it tries to increase the area. There may be a gradual increase in the area. So as of now, you just understand that nozzles and diffusers are the most common examples of flow devices in which the passage of cross-sectional area changes in the flow direction. Okay. Now we will move to the governing equations. Okay. Students, by governing equation, first one we know the conservation of mass m dot equal to constant, or rho av equal to constant, right? So this you know. Second one, for the conservation of momentum equation, you have already studied the Euler's equation, dp plus rho v dv plus g dz equal to 0 if the two sections are at height same height from datum, dz can be neglected. Dp plus rho v dv equal to 0. Third one, steady flow energy equation, SFFE. You have learned it is nothing but h plus v square by 2 equal to constant. So fourth one is entropy. Regarding entropy, here it is assumed as isentropic flow. Isentropic flow means entropy is constant. Entropy is constant. So these are the four different governing equations here. So these governing equations seem to be very simple for you. Why? Because we have made lot of assumptions. That is why these equations have been simplified to this extent. Actually, h plus v square by 2 equal to constant is steady flow energy equation, right, in one dimension. The actual conservation of energy equation is a very large equation. Actual momentum equation is a very large equation called Navier-Stokes equation. Actually, conservation of momentum equation is not a single equation. It has got three sections in real case. You won't be able to understand all those things. It will be understood only in your higher classes. For the time being, you try to understand that these are simplified to this extent using a lot of assumptions that we have discussed earlier. That is why it is seem to be very simple now. Okay. Now, now, now we can depict an isentropic flow process. Isentropic process on a Mollier diagram. What is a Mollier diagram? Mollier diagram. Mollier diagram is nothing but enthalpy entropy graph. Enthalpy entropy graph. That is nothing but Mollier diagram. Okay. So let us consider the flow of a compressible fluid from a large reservoir through a variable duct. Okay. Satisfying the isentropic conditions. So here we have a large duct. Okay. So from this large duct, it is flowing through a variable area duct. Variable area duct. So this is our reservoir. Okay. From this reservoir, the fluid is flowing through a variable area duct satisfying isentropic condition. Isentropic condition means all this duct is insulated. Okay. So there is no Q equal to 0. There is no heat transfer. Okay. So here since the flow through the duct is isentropic, the state of the fluid inside the tank where the fluid is at rest represents the stagnation condition corresponding to each location in the duct. So what is it? Since the flow through the duct is isentropic, the state of the fluid inside the state. So here students, here velocity equal to 0. It is a reservoir where the fluid is stored. So initially in reservoir the fluid is at rest. So velocity equal to 0. Okay. So if the velocity is 0 means and the flow is isentropic. The velocity of fluid at reservoir is 0 and the flow through the duct is isentropic. Therefore, the state of the fluid inside the tank where the fluid is at rest represents what condition? The stagnation condition corresponding to each location in the duct. The stagnation condition you have learned in your previous module. What is stagnation condition? Stagnation condition is that condition, that hypothetical condition, which is reached when the fluid is isentropically decelerated to 0 velocity. So the same is the case here. Here velocity is equal to 0. The flow is isentropic. So the pressure corresponding to this reservoir is P equal to, it can be the same as stagnation condition, P0, T0, rho 0, H0. So these are the conditions corresponding to the reservoir conditions can be the same stagnation condition. Okay. So knowing the stagnation conditions, also known as reservoir conditions, the mass flow rate and the cross-sectional area, the state of the fluid and its velocity at all downstream location can be estimated using the governing equations. So students, let P0, P0, T0, rho 0, H0 be the conditions of the fluid in the reservoir. Okay. So the state can be represented in thermodynamic coordinates if any two of the parameters are known, right? So in our HS diagram, or Mollier diagram, if we have two parameters, we can mark the state of the parameter. So the initial pressure P0 we know, initial enthalpy H0 we know. So corresponding to this first position, zeroth position of the reservoir position is no. So this is our first position. Okay, hence knowing H0 and P0, the stagnation state 0 can be represented in our modular diagram. Similarly, any downstream location in the flow. Okay, so here I am taking a section 1. So here P1, T1, rho 1, H1. So these are the conditions. These are the properties at section 1 in downstream. So flow is taking this way. So this is the downstream direction. So any downstream location the flow can be located directly below the stagnation point. Why? Because where can we mark 1? Directly below, because since this is isentropic process, we can draw a vertical line downwards, right? So this is this can be point 1 and another point 2 can be 1. If again you draw towards downward, it can be 2. So we can locate any downstream point location the flow can be located directly below the stagnation point, since for isentropic flow the flow remains constant. So S equal to S0 itself. Any S can be same as that of the entropy corresponding to the stagnation entropy. So this is how we mark. So this will be P1 and this will be H1, this will be P2, this may be H2. So any downstream location will be directly below, vertically below the stagnation or the reservoir condition. So that is the peculiarity of isentropic flow, right? Isentropic flow, because entropy remains constant. Entropy remains constant. S equal to S0, it always remains constant. So using the governing equation, state 1 and 2 in isentropic flow along the stagnation state 0 are established and shown in the HS diagram. So students, what is the difference of H0 and H1? We know the difference, the governing equation H plus V square by 2 equal to constant, right? That means H0 plus V0 square by 2 equal to H1 square plus V1 square by 2, right? Since V0 is 0, there is reservoir condition or stagnation condition, V0 is 0. H0, sorry, this is not H1 square. H0 minus H1 equal to V1 square by 2, right? H0 minus H1 is V1 square by 2. So you can mark here, this is H0, right? This is H1. So this difference is nothing but what? V1 square by 2, right? Similarly, what will be this difference? H0 and H2? V2 square by 2, right? V2 square by 2. So the difference will be V1 square by 2 and V2 square by 2. What will be this difference? What will be this difference? V1 square minus V2 square by 2. Okay. So you have understood to calculate the difference between the enthalpy. Difference between the enthalpy at any two cross section. So this the difference between enthalpy 1 and 2 is nothing but V1 square minus V2 square by 2, or V2 square minus V1 square by 2, right? So V2 square is higher, V1 square is lower. So this is a smaller value, this is larger value, right? Because towards the downstream direction, velocity is increasing, right? Velocity increases. Velocity increases. Therefore, V2 square is higher. So this is V2 square minus, I will show you once more. So this difference is nothing but V2 square minus V1 square by 2. Okay. Here it is V2 square minus V1 square by 2. So students, hope you have understood this basics of isentropic flow and how to depict it in your Mollier diagram or just diagram. Okay, actually there may be two types of flow. First one is expansion flow and compression flow. How it is different? Expansion and compression. Expansion and compression. So expansion means pressure is decreasing and velocity is increasing. Compression means pressure is decreasing, pressure is increasing and velocity is decreasing. So that is a difference here. Pressure increases, velocity. Sorry, pressure decreases, velocity increases. Here, pressure increases, velocity decreases. So I will show you the expansion and compression process in HS diagram. Okay. Suppose we have a flow. So this is the reservoir. Okay. Here V equal to 0, P0, T0, H0, rho 0. So section 1 here, section 2 here. So here P1, H1, P2, H2, V1, V2. Okay. Flow is taking place in this direction. Suppose this is our HS diagram. So this is P0 and this 0, H0. So let us consider an accelerating flow from section 1 to 2. So suppose the flow is accelerating. It is not necessary that flow should accelerate downstream. It can be decelerating also. It depends upon the area change. Depending upon area change, that you will learn in next class. Okay, how area change affects the nature of flow. Now suppose depending upon area change, flow can be accelerating, maybe accelerate or decelerate. Okay, so suppose it is accelerating from 1 to 2. So accelerating from 1 to 2 means, since the flow is accelerating, the velocity at the initial section 1 will be lower than 2, right? So V1 will be less than V2 because it is accelerating from 1 to 2. So 2 will be having higher velocity than 1, right? So we can mark V1 is higher means static enthalpy H0 equal to H1 plus V1 square by 2, right? H0 is also equal to H2 plus V2 square by 2. So stagnation condition, reservoir condition is same for any section at a downstream. The stagnation condition is same, H0 only, or reservoir condition is same only. So if V1 is lower means H1 is higher. If V2 is higher means H2 is lower, right? So here H1 will be closer to H0 than H2. So here H1 you can mark, here P1, and this is 1 and this is 2, P2, H2. So H1 will be greater than H2. If V1 is less than V2, H1 will be greater than H2. So this kind of flow work from 1 to 2, the flow accelerate means at a cross section 2, pressure will be lower than P2 will be lower than P1, right? P2 will be lower than V1 means the pressure is decreasing, velocity is increasing. So such kind of flow is nothing but expansion flow. So in expansion flow, P2 will be at a lower position than P1. Now you just think another case, HS diagram, H0. So this is P0, this is H0, and suppose V2 less than V1. V2 less than means decelerating flow. So so here we are having a decelerating flow. Suppose due to some kind of area change from 1 to 2, flow gets decelerated. Flow gets decelerated means the velocity is decreasing. So velocity decreasing means initial velocity is higher. Section 2, at section 2 final velocity will be lower. So means what will be the difference, what will be the relationship between the static enthalpy? H2 will be greater than H1. If V2 less than V1 means H2 greater than H1. So 2 will be closer to H0. H2 will be closer to H0. So this is P2 and this will be 2 and this will be 1, P1, H1. So if 2 is higher, 2 is at higher value than P1, this kind of flow is nothing but compression flow. So this is expansion, because here P increases, V decreases, right? So such a flow is compression flow. Compression flow is depicted in this manner. Sorry, here actually the direction is 1 to 2, this manner, okay? Here, sorry. This is expansion, right? Expansion 1 to 2, this manner. In compression 1 to 2, the direction is upward direction. Okay, I will mark in using. So this is in compression the direction is upward, in expansion direction is downward, 1 to 2 downward, here 1 to 2 upward. Okay, so that is the difference in showing expansion and compression and a Molière diagram. Now you just need to know this difference is nothing but V2 square minus V1 square. V2 square minus V1 square by 2, because V2 is higher. Here what is this difference? V1 square minus V2 square by 2. Why? Because V1 is higher. So that is the difference. Okay. So that is the difference. So for the time being, I am stopping this session. Thank you.